This video is going to discuss the Grignard reaction, which, if you haven't seen it before, happy to introduce it to you. For many undergraduate organic students, this is the first organometallic reaction that you have the opportunity of being exposed to. So we're just going to dive right in, and then later we are going to discuss something called protecting groups. And this does have a direct application to the Grignard reaction, but again, we're going to get to that a little bit later. Let's get into the chemistry right now. The Grignard reaction allows for addition and substitution with carbon-based nucleophiles. And this is interesting because, right, so back when you learned SN2 reactions in undergraduate organic chemistry, you did something called the Williamson ether synthesis. That's where you had this alkoxide, right, this nucleophilic atom that attacked an electrophilic carbon on an alkyl halide, usually an alkyl bromide, primary alkyl bromide at that. So this is really cool that we can actually have a carbon nucleophile. And these are run in anhydrous conditions, but we're going to talk about why that is later. So we have this organomagnesium organometallic reagent called the Grignard reagent. And the formation of the Grignard reagent happens when you mix some alkyl or vinyl halide, now vinyl being whether it's just next to a double bond or maybe it's a benzene ring, maybe it's bromobenzene, alkyl bromide in, with literally magnesium turning. It's quite literally the metal, and it's going to turn this brown color, and it's going to get really, really cool. And the magnesium actually inserts itself in between, right here, the R group and the bromine. Now I'm just using X just for the sake of the argument, but you get something that looks like this. All right, so if we were to do this on this real life example right here, we would just draw our 1, 2 carbons and then insert our magnesium. You know, instead of a carbon-bromine bond, we now have a carbon-magnesium bond and an ionic magnesium-bromide bond. So we would draw our 1, 2 carbons, then we'd have MgBr, or you can just write that as. Everyone pretty much understands that you're denoting an ionic bond there. So when we have this nucleophilic addition of the organometallic reagents, when we react these with aldehydes, we primarily get secondary alcohols, and by primarily get, I mean we get secondary alcohols, period, end of sentence, end of story. When we react ketones with these reagents, we get tertiary alcohols. And just a note, you know, and we'll notice this on the next page actually, but you'll notice that if we add 1, 2 carbons on to this molecule and this becomes an alcohol, right? 1, 2 carbons, 1, 2 carbons. This carbon is not chiral. Okay, 2 of the substituents are the same. So 1, 2 carbon chain, 2 carbon chain, 2 of the substituents are ethyl chains. It's fine. But if you are adding an alkyl chain on, or any type of chain on for that matter, you do need to worry about stereochemistry, and racemic mixtures often will result from these reactions if this does not match the carbon chain that's already on the molecule. So with that being said, let us draw the product. Remember that we're going to get a secondary alcohol if it's an aldehyde, tertiary alcohol if it's a ketone like we have here. So we're just going to merely add this 2 carbon chain on. So we'll redraw our benzene ring. And that is all we have to do. And you can put for the OH, you can put the hydrogen here, just show that the oxygen is bonded to the carbon. And for the sake of it, we'll put our lone pairs on the oxygen. So that's the product. But let's talk about the mechanism of the Grignard reaction. It's actually quite straightforward. You'll see that step 1 is adding the Grignard reagent. So we're going to zoom way in here just so you can see what I'm talking about. Step 1 is adding the Grignard reagent to your starting material. Step 2 is quenching the reaction with water. And we said that this had to be run in anhydrous conditions, meaning that when we add the Grignard reagent to our starting material, the water, it's very essential that water isn't present in the reaction mixture at all. And we're going to get to that and why that is in a little bit. But let's draw the mechanism for the Grignard reaction. And just recalling parts and mechanisms of other carbonyl addition reactions, remember that basically implies that the reacting carbon is going to be this carbonyl carbon right here. So what's interesting about this reaction, again, we said it was carbon nucleophiles. You're actually going to draw your arrow from the center of this carbon-magnesium bond. So we're going to draw an arrow from the center of the carbon-magnesium bond attacking the carbonyl carbon. One of those bonds will break onto the oxygen. So we get this. I'll actually redraw that first ethyl chain a little bit differently just so you can see. Now, when we add that water in after our Grignard reagent is added, you'll see why. Of course, water is going to act as a proton source, and we're going to protonate this oxygen so we get our final product. Sorry, I'm just trying to draw that so it's really clear. So, that's our final product. So 2 steps: attack of the carbonyl carbon from the center of that carbon-magnesium bond, and then protonation of the oxide with some water. Not too bad, right? Not bad for your first organometallic reaction. So let's look at why we really can't run this reaction in anhydrous, well, let me rephrase that. I got a little bit jumbled. Why we can't have water in this reaction mixture and why it must be run in anhydrous conditions. So if we ran this reaction, and actually I should draw this again. I'm gonna redraw it up here. Let's say we ran this step 1, step 2, Grignard reagent, and then water. Okay, we would get a mixture of products, a racemic mixture, obviously, right? So we'd be making a bond between this carbon and that carbon. That would be a racemic mixture. We have a single bond here, carbon-carbon double bond there, so we do not have the same substituent, or 2 of the same substituent on that carbon right here. So we will get a racemic mixture, and that will be this. And I'm just going to draw 1 enantiomer right there, and I'm going to write racemic. So remember, that means that you're going to get both enantiomers, so then this would be on a wedge and this would be on a dash. Remember, enantiomers have identical chemical and physical properties, and they are just the inversion of stereochemistry at all stereocenters. They're non-superimposable mirror images of each other. So just a quick review of enantiomers for you, in case you hadn't heard that recently. I'm sure you have, but just in case. So let's look at this right here. And if you actually run this reaction, and you added water in at first with your Grignard reagent, you would get the same thing back out of the flask. So you run the whole reaction, you're ready to do your workup, you isolate your product, and you realize it's the same as your starting material, right? No reaction. So why is this? Well, let's take a look. Remember, let's say we have the Grignard reagent and water by itself. So we're just going to act like this doesn't even exist, right? So we have our BrMg, right, and we have our H2O. Remember that this carbon-magnesium bond is kind of nucleophilic, and that's really what does the attacking of the carbonyl carbon when the Grignard reaction is performed by adding the Grignard reagent only first and then the water. So tell me why this is not an appropriate mechanism, and by this I mean, why wouldn't it just steal a hydrogen and we'll draw our equilibrium arrows for the sake of it, and bubble out as ethylene gas, right? Because we would also get this MgBr. Now this is just saying that obviously when magnesium's an ion, right, +2, Br is -1, so this whole thing has a positive charge, and we knew implied that bromine had a positive charge, and obviously you get this OH- out of the water. Now, if this isn't rational enough for you, recall that the pKa of water is about 15.7, pKa of ethylene gas is about 40. So right away, you know equilibrium tends to favor the side of the reaction with the higher pKa, right? So equilibrium is going to favor the product side with this bubbling out of solution as a gas. Now, obviously, once it bubbles out of solution, it's not really going to be back here to try and push the equilibrium back this way either. So that is why these reactions need to be run in anhydrous conditions. Absolutely, absolutely. So let's take a look at, let's just sum that up first. Remember that anhydrous means that we can't have water in there while the addition of the reaction at least is actually running. So that first step needs to run. So remember, stepwise addition, good. Adding them both together leads to no reaction. You get your starting material back. Let's go through now a Grignard reaction with something called a hydroxyketone. So a ketone with an alcohol present. And just for the sake of example, here's a hydroxyketone. Yay, there it is. So let's go through the mechanism first, actually, and then we're going to draw the product up here. So I like to do, if you've watched any of my other organic videos, I like to draw the overall product up here and then the mechanism down here, so we get a sense of what the reaction should be, and then we justify it and we rationalize the overall product that we've drawn at the top. I actually would like to draw the mechanism first because that's going to give rise to the overall product, so I'd like to kind of derive it. So let's just recreate what we have here, and actually, for the sake of the example, let's make this an aldehyde. It was an aldehyde originally on my notes, and then it turned into a ketone on ChemDraw somehow. So let's just make it into an aldehyde. And actually, let's draw in this oxygen-hydrogen bond. We'll draw our lone pairs on, like good chemists. So I think something, at least you've noticed, something similar is going to happen here as to what happened, to a reaction when it was run with water. We're going to get this alkoxyketone plus, ethylene gas bubbling out of solution. Great. So then when we add the water in, rather than protonating this ketone being refunctionalized into an alcohol, we protonate this alkoxide to give rise to our final product, which is the same as our starting material. So no reaction. So how do we deal with this problem? Does this reaction just completely lose its functionality and its efficiency or productivity if we have more than one functional group? Well, of course it doesn't. Of course there's a super fun workaround, and those are called protecting groups. And protecting groups basically defunctionalize some functional group that would react in a way that you don't want it to react. Let me simplify that, because I realized that kind of was a jumble of words. Basically what we're going to do is if there's another functional, so we have an ideal functional group that wants to react, right? In this case, we're going to have the same thing, and this is going to become an aldehyde again. The functional group we want to react is this ketone. Now, we have an alcohol sitting on this side of the molecule. Now, obviously, we don't want to leave this alcohol in the molecule like this. We want to be able to honestly be able to shield this from reacting at all. So basically what we want to do is we want to close it off to other reacting environments. So we do this by putting a protecting group on it, and there's there's a couple things, so it needs to be easy to put on, easy to take off, and they're commonly silyl ethers. And by silyl ethers, I mean we're going to treat it with something called trimethylsilyl, or TMS, chloride. And the oxygen is obviously more reactive than the chlorine, so oxygen's going to steal the chlorine spot, chlorine's going to pop off, and everything's going to be fine. So let's go ahead, and we're just going to draw the overall reaction process first, and then we're going to go ahead and do the rest of it. So if we treat our hydroxyketone, or hydroxyaldehyde, with TMS chloride and TEA, or triethylamine, any base really, to deprotonate that oxygen after it attacks the silicon, we then get a product that looks like this. Right, so we have O, and then we're going to put that TMS, or trimethylsilyl, on the oxygen. So O, TMS. Okay? Now, please, what if the molecule was oriented the other way? Let's say we wrote OTMS. Okay, this is wrong because you're noticing the oxygen still needs to be bonded to the carbon. So if you're writing it the other way, and this is just more of a syntax thing, but I figured I'd talk about it, right? You'd write it as TMSO, just showing that the oxygen's still bonded. Okay, anyway, so then we would perform our Grignard addition, right? So we would get this, and I'm going to put racemic. And then finally, we would do something called a deprotection step, which is used, which uses TBAF. TBAF stands for tributyl ammonium fluoride, so it's an ionic compound more or less, and it looks really ridiculous, and I'll draw it for you here in a second. But it's just any real source of fluoride, so that F minus there is what's going to help us along. So after we treat it with TBAF, we get this. Racemic. TBAF, so I just want to draw it because it's fun. So tributyl, or tetrabutyl, I'm sorry, definitely tetrabutyl. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Nitrogen's got a positive charge. Fluorine's obviously got a minus charge. So there's our tributyl ammonium fluoride, that is TBAF. So that fluoride right there is what assists in the deprotection. So let's go ahead and draw through the mechanism. And in a general sense, it's not common that as an undergraduate organics student that you'd need to know the mechanism, but I'd like to use kind of just some familiar chemistry to explain how this actually works on a molecule. So let's go ahead and do that. So we're going to redraw, pen. So we said we were going to treat it with TMSCl to perform the protection step in ET3N or TEA. So just in case you've seen it written this way, I personally prefer writing it as TEA because it's T, and I can remember that really easily, and hopefully you can too. So we're going to treat it with this silicon with 3 methyl substituents and a chlorine. So each here, you CH3, CH3, CH3. What's going to happen is the oxygen from this lone pair is going to attack the silicon. Chlorine's going to pop off. Right? So now we get this here. this hydrogen on, lone pair. Cool. I was one step ahead of myself. So then our TEA is going to come in. So triethylamine, I'm sure you can imagine, is an amine with 3 ethyl substituents. It's going to serve as our base. It's going to deprotonate. So we can get this. And if you haven't seen this before, by the way, these 3 lines stacked on top of each other, it's basically a chemistry equals sign. So that's our protection step right there. So we get an attack of the silicon, chlorine pops off, and then we get deprotonation with TEA or triethylamine to give us our silyl ether protecting group. So ether, right, functional group. Let me get the pointer. So ether is that functional group, that single bond embedded oxygen. So we call it a silyl ether because there's a silicon on one side of the oxygen. You can also just denote it OTMS. So then we perform our Grignard reaction, but it's a great time to practice our mechanism. So let's practice our mechanism, and I'll actually even write step 1. So here's step 2. Go here. I believe that's the reagent I used. Yes, it is. So remember, we're going to get from the center of that carbon-magnesium bond, and I'll draw it right to the carbonyl carbon. It's going to get an attack right there. And then we're going to add in some water. To protonate this oxide. So then we've successfully completed our Grignard reaction. Without having that alcohol reacting being an issue, right? Because it's not there. And I'm going to write racemic here instead of drawing the other enantiomer, just to save a little bit of time and space for all of you watching. So the last step is the deprotection step. Again, this uses TBAF. Really, all you have to worry about in TBAF is that fluoride ion. So we're going to draw step 3. So now we've got our Grignard product. We're going to put racemic. So we have this fluoride floating around, really, really reactive. And what the fluoride's going to do is take oxygen's place on the silicon. So it's going to do exactly what oxygen did to the chlorine. Now, actually, let's draw it in from another side. There we go. And then what we're going to do is have some water come in. To be a proton source for that alkoxide. So then we get back our alcohol on one side with our Grignard product. Yay! So, that right there is the full mechanism for a TMS chloride protection of an alcohol to allow this aldehyde to undergo a Grignard reaction. And just public service announcement, we can definitely rotate this bond right here. Well, I suppose it's actually this bond. But you could also write this product as this. But that's not that important. Really, you want to just stick to it. I just always like to write my chain that I added with the Grignard gradation, give that stereochemistry, and leave everything else the same to mitigate chances of being wrong-o on an exam. But anyway, I hope you enjoyed this video. I hope it gave some rise to interesting chemical ideas to do with an organometallic reaction that you have the opportunity to be exposed to in undergraduate organic chemistry. And we will see you next time.